Hi everyone. So in this video, I'm going to be going over some of the questions from the review. And so today's video is going to cover questions that were requested up to everything including trig, basically. So ending around question 9 on this review. And then in tomorrow's video, I'm going to cover questions that come from the second part of the review packet. So stuff about polar coordinates, about conic sections, and any kind of the 141 review. So the first question that was requested was number 2. So number 2 is just asking you to say, what is the domain and what is the range of these different functions? So why am I asking this question? It's basically because I really want to make sure that you understand kind of how these functions work, how trig functions work. You know, what kind of things are you plugging in and what kind of things are coming out? So in general, like just taking kind of a step back, what does it mean? You know, what is the domain of a function? Of any function. So the domain is the set of all values that can be plugged in. I'll say that as the set of all inputs. And basically you're thinking about like what types of numbers can be plugged in. And then what is the range of a function? Well, the range of a function is the set of all outputs. And so when we say outputs, we basically mean what kind of numbers can come out of the function. So we'll get to the specific answers for those, all the different functions I listed in a second, but kind of like another big picture thing to think about is that when you have a regular trig function. So when I say a regular trig function, I mean not inverse trig, right? Things like sine of x, cosine of x, tangent of x, cosecant of x, any function that is not inverse trig. What kind of a thing do you plug in? So you plug in an angle, right? You take sine of pi over 2. You take tangent of pi over 6. You're always plugging in an angle. And then what kind of a thing comes out? Well, it's a number. And technically an angle is a number too. But I'll say it like this. I'll say it's a ratio, right? It's a number that specifically results either from looking at, maybe opposite over hypotenuse, or looking at a coordinate on the unit circle, or doing, y over x. It depends on the trig function, but you're doing some kind of a ratio related to that angle. And then for an inverse trig function, what kind of a thing are you plugging in for that? Well, it's the reverse now, right? Now your input is a ratio, so it's a number. And the output is going to be an angle. So I'd say of everything that we're going to discuss in this question, this is kind of like the most important part. This is what I just really, really hope that everyone who took this class understands before moving on to the next class. This kind of just big picture, how trig functions and inverse trig functions work. Okay, so let's get a little bit more specific with the specific types of trig functions. So we have f of x is equal to sine of x, g of x is equal to cosine of x, and h of x is equal to tangent of x. And I think I called them all f of x in this problem. Doesn't really matter. So what is the domain of sine? So what kind of angles are you allowed to take sine of? So there are no angles that you cannot take sine of, right? You can go to any angle on the unit circle, and you can go around the circle as many times as you want. You can go backwards, any angle. You can plug in -1,000,000 pi, right? And that will still, you can still find what sine of that is. So the domain is -∞ to infinity. You can plug in any angle you want. So what about the range? Well, what kind of numbers come out? So remember, going back to what do domain and range mean? you're thinking about what kind of numbers can come out of your function. And so when you take sine of an angle, you're never going to get anything that is smaller than -1 or bigger than 1, right? So the outputs are stuck between -1 and 1. And similarly, cosine is the same deal, right? You can plug in any angle you want, and then the output is going to be a number between -1 and 1. So why are the outputs always between -1 and 1? Well, if you think about the unit circle definitions of sine and cosine, you're giving x coordinates and y coordinates. And when you're on the unit circle, those x and y coordinates are just never going to be bigger than 1 or smaller than -1, right? The definition of the unit circle is that it has a radius of 1. So you cannot get an x or y value that is bigger than 1 or smaller than -1. We can visualize this by looking at the graphs of sine and cosine. So here is the graph of sine and here's the graph of cosine. Both of these, their domain is all real numbers, right? You can plug in any number you want, going all the way as far to the left or to the right as you want. But the range, they're stuck between 1 and -1, right? There's no way for them to get bigger than that. So for tangent's a little bit different. So what's the problem with tangent? Well, tangent, you calculate it by doing the y coordinate over the x coordinate on the unit circle. And so basically tangent is going to be undefined. So maybe I'll write this out first. I'll write it down here. So tangent is undefined whenever cosine of x is equal to 0. So why am I saying that? It's because when you're at an angle, so how does tangent work? You're doing sine over cosine, right? Or y over x. And so if cosine is 0, then you get something that's undefined. So what are the angles that makes that happen? Well, basically any odd multiple of pi over 2. So x is not equal to pi over 2, 3 pi over 2, 5 pi over 2, etc. And so another way to say that would be, and I can't remember, how did I say it in the solutions? Because there's a lot of different ways to say it. I would just say x is not equal to odd multiples of pi over 2. There's a way to say it in interval notation, but it's kind of complicated and it's just really not worth it. So I would just want you to know that tangent is not defined anytime you try to take tangent of pi over 2, 3 pi over 2, -3 pi over 2, 7 pi over 2, any odd multiple of pi over 2. So the other thing that's different with tangent is that tangent is not just equal to the x coordinate or the y coordinate on the unit circle, right? So that means that it's allowed to be bigger than 1 and smaller than -1. So one thing that we talked about in this class is how tangent is really equal to the slope of the line that you're drawing on the unit circle. So that's another way to, by the way, to see that it's undefined at these values. So for example, if you go to pi over 2, a vertical line has an undefined slope. And if you go to 3 pi over 2, same problem. So basically you can get any slope you want, right? Like if you're down here, your slope is 0, your slope gets a little bigger, a little bigger, a little bigger, a little bigger. And then going, if you go to almost vertical, that's going to be a really, really, really big slope. And then looking at negative numbers, here you have a small negative number, smaller, smaller, smaller. And the more and more you get closer to vertical, the more and more of a negative, you'll have like -100 or something like that. And so that means that we can actually get all real numbers as our range. And that shows up in the graph as well. So if we look at the graph of tangent, so first of all, it has vertical asymptotes at all these odd multiples of pi over 2, right? Negative pi over 2, pi over 2, 3 pi over 2, etc. And then it also it goes up and up and it goes down and down. So that is another way of seeing that the range is all real numbers. Okay, so let's talk about the inverse trig functions now. So starting with, and I'll just say f of x again. So f of x is equal to inverse sine of x. So with inverse trig, now things are kind of reversed. So what kind of a thing are you plugging in? Now you're plugging in a ratio, a number, and your output is going to be an angle. And so what kind of a number are you allowed to plug into inverse sine? Well, you can't take inverse sine of any number that is smaller than -1 or bigger than 1, right? Because if you just think about what is the definition of inverse sine, it just doesn't make sense. Like if you tried to take inverse sine of 2, that would be asking you for an angle such that sine of that angle is 2, and that isn't possible. Another way of seeing this is that the domain and range of inverse functions are swapped, and so that's why the domain ends up being -1 to 1. So the range, I know I just said the domain and range swap, but remember that when you have inverse sine, it's not technically the domain of this function, it's the domain of a restricted version of this function. So if you think about inverse sine, we know that only certain types of angles can come out from inverse sine. Specifically, inverse sine will only give you angles between -π/2 and π/2, right? Because, and that's why it's the range. The range is the set of all the numbers that could come out. Anytime you do inverse sine, it's never going to give you an angle that is not between -π/2 and π/2, and that tells you that that is the range. So domain is the inputs, range is the outputs. So similarly, if we look at inverse cosine, the domain is the same, right? Because same with inverse sine, you can't take inverse cosine of numbers that are outside of the range of cosine. So what is the range for inverse cosine? Well, now when you're doing inverse cosine, that always gives you angles between 0 and pi. So it's different from the range of inverse sine. And then finally for inverse tangent, well, because because regular tangent has a range of all real numbers, inverse tangent has a domain of all real numbers, right? Because you can take, how I wrote down inverse sine, so earlier I said this, inverse sine of 2 does not exist, right? Because it's not possible to find an angle such that sine of that angle is 2. However, inverse tangent of 2, that does exist. I don't know what it is. You would have to type it into a calculator, but it does exist because it is possible to take tangent of an angle and get something that's bigger than 1, because tangent is just fundamentally different from sine and cosine. And so that's why the domain is all real numbers. And then for tangent has a similar range to inverse sine. The only difference is that because tangent is undefined at -π/2 and π/2, we don't include those in the range. Okay, so let's look now at number 3, which is actually kind of related to this one. So number 3 is asking you, does the point -π/6, -π/6, let me fix that, √3/2 lie on the graph of f of x is equal to sine of x. So again, this is a problem where I'm really testing whether you understand what these functions mean. So the biggest mistake I see people make on this is you get the graph confused with the unit circle. So the unit circle is a tool. It's a tool that helps us evaluate sine and cosine of different angles. The unit circle is not the graph of sine of x or cosine of x. It's a tool that kind of has all the information we need to find all the trig functions, but it's not a graph of any of the trig functions. So how do functions work in general? Well, like just to give a total side example, if I asked you, does the point, let's say 1, 2, lie on f of x is equal to x squared, how would you check that? Well, you would plug in 1 for x, and you would get 1 squared, which is 1, and that is not equal to 2, right? So your answer would be no. So if you're asking whether a point lies on a graph, you're just basically checking, like, if I plug in the x value, do I get the corresponding y value? And so in this case, what we need to check is is it true that f of -π/6, we want to check, does that equal √3/2? So what is f of -π/6? It's equal to sine of -π/6. And so sine of negative pi over 6, we would find that by going to an angle of negative pi over 6. So that would be like down here. And the x coordinate is square root of 3 over 2. And the y coordinate is negative 1/2. And so sine of negative pi over 6 is equal to negative 1/2. And negative 1/2 is not the same as square root of 3 over 2. And so that tells us that the answer is no. Okay, so next question, similar, is asking, does the point pi over 4 square root of 2 over 2 lie on the graph of f of x is equal to inverse sine of x? So this one you can actually answer without even kind of going through this plugging in business. And the reason that you can answer it without that is just going back and thinking about this, the stuff that I put in the bubble here. So whenever you have an inverse trig function, you should always be plugging in a ratio, and then your output should be the angle. And so if we look at this, this point that we're looking at, so if we look at this point, the input is an angle, and the output is a ratio. And so that doesn't fit with inverse sine, right? Inverse sine is supposed to have an input of a ratio and an output of an angle. And you could even, I mean, you could try this, but it just doesn't even make sense. Like, you would need to check, so if we do f of pi over 4, that would be inverse sine of pi over 4, and that just doesn't even make sense. I mean, you could type this into a calculator because pi over 4 is a number, right? So you would get some number and you could take inverse sine of that number, but it just doesn't mean what you think it does. Like, the answer for inverse trig is supposed to be an angle, so it doesn't make sense to plug an angle into inverse sine. So I'll just write, does not make sense. So really what's going on here is that the point pi over 4 square root of 2 over 2 does lie on the graph of f of x is equal to sine of x, because if you plug in pi over 4 into sine of x, then you get square root of 2 over 2. So I was kind of trying to trick you because it, it's related, but it doesn't lie on the graph of the inverse trig function. Oh, and I think I had my numbers wrong. This was supposed to be number 4, my bad. Okay, so next we're going to look at some graphing. So this is number 5. So we're not going to do all of them. We're going to do C and D. So C is h of x is equal to sine of x minus pi over 4. So before we get into sketching the actual graph, let's put down the graph of just like one cycle of sine of x so that we can then kind of compare. So what does sine of x look like? Well, it has a period of 2 pi, right? So it starts at 0 because sine of 0 is 0. And then anytime you're sketching a trig function, wherever it kind of starts its cycle, it's going to end the cycle at the same height at the end of that period. So because the period of regular sine of x is 2 pi, if it starts at a height of 0, it's going to end at a height of 0. Then trig functions are very symmetrical. So sine of x is going to go through 0 exactly halfway between 0 and 2 pi. Then it's going to hit its highest point halfway between those two and its lowest point halfway between the other two. And so that means that the graph of this is just sine of x. Again, this is not, this is not the transformed function yet. I didn't do the best job drawing that, but this is just f of x is equal to sine of x. Okay, so now that we have this drawn, now we can think about, how does this graph compare to sine of x? Well, this one has been shifted to the right. So this is a shift to the right by pi over 4. And so how do we know it's a shift? Well, anytime you're adding or subtracting a number to a function, that's basically just taking all of your inputs or outputs, depending if it's a horizontal or vertical shift, and it's just kind of adding or subtracting one to them. And so that's not going to change the shape of your graph. It's just going to kind of pick your graph up and move it and slide it one way or the other. So in this case, we're just going to take every point on this graph and move it to the right by pi over 4. And we don't have anything else going on here, right? We don't have a number out front. That would be a vertical stretch if there was something there. If we had a number here, that would be a horizontal stretch or compression. If we had like +1 here, that would be a vertical shift. But all we're doing in this case is shifting to the right by pi over 4. So we're going to take every point on this graph and just slide it over by pi over 4. I guess I didn't print graph paper that was like quite detailed enough, but we know pi over 4 is just halfway between each of these boxes. So I'm just going to take each of these points and slide it over. So that would give us, then it's going to end its cycle here. And so the graph is going to look like this. And you could do this without actually first drawing the graph of sine of x. I mean, basically, the main reason I drew the graph of sine of x was so that we had like the shape drawn, because I think it's really important to know what the shape of sine of x looks like. But really, when you're graphing this, what would you have to think about? You would have to think about where does the cycle start and where does it end? And so because everything's been shifted to the right by pi over 4, we know it starts at pi over 4 and ends at 2 pi plus pi over 4. And then you could just use symmetry. You could say, okay, well, it's going to go halfway through, or it's going to go through the x-axis halfway between those and put a point here. And then do halfway for the top point and the bottom point. So you don't always have to like go from scratch and draw the original function. I think the better way to do it is to think about where is your graph kind of starting and ending, and using symmetry to fill in the pieces between. Okay, so next one we're going to look at is D, and I swear, there it is. I knew I copied and pasted the axes. So D is k of x is equal to negative sine of 1/2 x. Okay, so again, we have a sine graph, right? So we're going to have the same kind of basic shape that we did in the last one. In this case, what's going on? Well, we have a vertical reflection, right? So when you have a negative sign out front, that means that you're taking all of your outputs and changing their sign. And so that's going to take the graph and it's going to reflect it over the x-axis. And then what is this 1/2 going to do? That's going to be a horizontal. So anytime you're multiplying x by a number, it's going to be a horizontal either stretch or compression. So remember that if this number is smaller than 1, it kind of goes backwards of what you'd expect. So this is actually a horizontal stretch by 2. So what you want to do is take the reciprocal of this number, and that will tell you kind of what's going to happen horizontally. And so what does that tell you? Well, the period, instead of being 2 pi, is going to be 4 pi. It's going to be twice as much. And you could also have done that by, remember the kind of general rule is you take 2 pi and you divide it by whatever this number is. So you could do 2 pi over 1/2, and that would give you 4 pi. Or you can just think, oh, it's been stretched by 2. Okay, cool. That means that it's twice as wide. Okay, so this one, let's try to sketch it without drawing the graph of sine of x first. So it hasn't been shifted horizontally at all or vertically at all, so it's still going to have a y-intercept of 0. It's going to start at 0. Then the period is 4 pi, and so that means that the cycle is going to end at 4 pi. And so halfway between those two, the graph is going to go through the x-axis again. And now we have to start thinking about those kind of peaks and valleys and where those are going to happen. So we want to check, first of all, is there any kind of vertical stretch? And there isn't, right? So the amplitude is still 1. The graph is still going to go to a maximum height of 1 and a minimum height of -1. The other thing we need to think about is the shape. So has it been reflected? And it has. And so what that means is that instead of going first up and then down, it's going to first go down and then up. And so halfway between 0 and 2 pi, we're going to have our minimum. And then halfway between 2 pi and 4 pi, we're going to have our maximum. And so the graph ends up looking like this. And I know that the graph kind of looked a little different in the solutions, and that just has to do with the scale. So on the solutions, the grid that I drew it on basically just had a different scale. So it made it look kind of flatter because the y-axis had more numbers on it. So don't worry too much about that. As long as your graph has the right period, the right amplitude, and the right kind of shape, then you should be good. Maybe without fully drawing them, let's just quickly mention kind of what's going on in some of these other graphing questions. So for the first one, which was 2 times cosine of x plus 1, this one is a vertical stretch by 2, right? So this is going to stretch vertically by 2, and then it's also going to shift up by 1. And so the midline is going to move, and also the amplitude is going to change. And then not this one, this one. So this one is also reflected over the x-axis, so it's going to have a negative of like the typical cosine shape. And then this one, because it's multiplied by 2 inside the parentheses, that's going to be a compression by 2. And so that one's going to have a period of just pi. And then finally, tangent of x, that is just reflected over the x-axis. Okay, so next we're going to look at a couple from number 6. So we've done a lot of these, especially things like B and D, but I want to look at A and C. Those are both requested, and I think those are both they're ones that we haven't done quite as much with. So first one was, so that's 6A. So 6A is asking us for inverse tangent of 1 over square root of 3, which could also be written as square root of 3 over 3 if you rationalize it. So this is basically asking us, so whenever you're doing inverse trig, it's asking you to find an angle. So we want to find an angle theta, and that angle theta should be between negative pi over 2 and pi over 2. And we want to choose that angle such that tangent of theta is equal to 1 over square root of 3. So how can we figure this out? Well, basically what I would think about is if you have a square root of 3 here, what kind of angles bring up square root of 3? They're multiples of 30 and 60, or pi over 6 and pi over 3, right? Like if you're taking, so whenever you're taking tangent, you're doing sine over cosine, or the y coordinate over the x coordinate. And if you're doing that with a multiple of pi over 4, you're going to get things, you're going to have square root of 2, right? And those are actually going to cancel out, and you're either going to get 1 or negative 1. If you're doing an angle like 0 or pi, then you're going to have tangent be equal to 0. So really the only angles that could possibly introduce square root of 3 are going to be pi over 6, pi over 3, or any kind of multiples of those. So if we think about, what is the part of the unit circle we're supposed to be looking at, the angle we need to find needs to be somewhere in here, right? It needs to be specifically actually between pi over 2, 0 and pi over 2, or 0 and negative pi over 2. So tangent is supposed to be positive, right? We're looking for an angle where it's positive. And so that means that we're kind of restricted to being quadrant 1. That's the only place that we're going to get a positive value for tangent. So what I would say is there's basically 2 candidates, and I would just try them both. The 2 candidates are pi over 6. So pi over 6 would have an x coordinate of square root of 3 over 2 and a y coordinate of 1/2. And then the other candidate would be pi over 3. And so this would have an x coordinate of 1/2 and a y coordinate of square root of 3 over 2. And to be honest, I don't even know off the top of my head, I'm sure if I thought about it for a little longer, I could figure it out, but I don't know off the top of my head which one it is. I really, really just mean trial and error. There's only really 2 things we have to try, so it's not going to be that much of an effort to figure out which one it is. So tangent of pi over 6 is going to be sine over cosine, so that one is going to be 1/2 over square root of 3 over 2. And so if we simplify this, the 2's are going to cancel out and we're left with 1 over square root of 3. So that's what we were looking for, right? If we had done tangent, and I'll just do this one too. So if we did tangent of pi over 3, we would have got square root of 3 over 2 over 1/2, and that would equal square root of 3. And so that's not what we're looking for. And so basically what we just figured out is that the answer is pi over 6, because pi over 6 is in the right part of the unit circle, and tangent of pi over 6 we just showed is equal to 1 over square root of 3. If it had been negative 1 over square root of 3 or negative square root of 3, then that would mean that we'd want to look for angles down here, right? We'd want to try negative pi over 6 and negative pi over 3. Okay, so next one. So this next one is asking us to find tangent of inverse cosine of 2/3. So there's a couple of different ways to do this. You could do it on the unit circle, and then you could also do it with a right triangle, and you're going to get the same answer either way. So maybe I'll show you both ways. Personally, I think the right triangle way is easier, so maybe let's do that first, and then I'll show you how you would get the exact same answer if you use the unit circle. So the main thing to realize here is that whenever you're doing one of these kind of composite questions, right, where you have like a trig function and an inverse trig function, the inverse trig function represents an angle, right? So here, this is some angle theta. So what do we know about theta? Well, we know that theta has to be between 0 and pi, right? Because it's inverse cosine. And because we're taking inverse cosine of a positive number, that actually means that theta has to be between 0 and pi over 2. So that means that we can fit this angle in a right triangle. And so if inverse, let me write this down here, we basically just said that theta is equal to inverse cosine of 2/3. And so what that means is that cosine of theta is equal to 2/3. And what is cosine? Cosine is adjacent over hypotenuse. So what that tells us is we can draw a right triangle, and we can put that angle theta in our right triangle. And that tells us that the adjacent side should have a length of 2, and the hypotenuse should have a length of 3. And in this question, what we're looking to find is tangent, right? So we're eventually going to need the opposite side. And so how can we find the opposite side? We can use the Pythagorean theorem. So we can call this b, and we can say 2 squared plus b squared is equal to 3 squared. And so that gives us 4 plus b squared is equal to 9. And so that means b squared is equal to 5. And so b is equal to the square root of 5. So now all we have to do is find tangent of theta, because if we go back to what the question was actually asking us, it was asking us to find tangent of this thing that was an angle. Inverse cosine of 2/3 is an angle. And so instead of writing inverse cosine, we just put theta there. And now we can use this right triangle to answer the question. So we want the opposite over the adjacent side, because that's how you find tangent. And that's going to be square root of 5 over 2. So how would you do this using the unit circle? It would be very, very similar, and I'm not going to necessarily do like the whole question this way. So this is like, let me just write here. So this is method 1. Down here, let me do separately method 2. And the reason I'm showing you this other method is I just really want you to understand that that right triangle trig and unit circle trig aren't fundamentally different. Like, they're compatible. The one thing is that there are situations where you can only use the unit circle, right? As soon as you're taking or you're doing trig with like negative angles or angles that are bigger than 90 or anything like that, then it doesn't make sense to draw a right triangle anymore. But as long as the angle you're dealing with is between 0 and 90 degrees, it's gonna be the same result regardless of whether you use a right triangle or you use the unit circle. So if we wanted to use the unit circle, it's basically the same idea. So we're taking tangent of inverse cosine of 2/3. And so we're calling that theta. And so basically, as we said earlier, that if theta is equal to inverse cosine of 2/3, that means that cosine of theta is 2/3. So what would that look like on the unit circle? Well, it would mean that we have an x coordinate of 2/3. And so I don't know, maybe that's somewhere over here. So we could go to our angle, and this would be the angle theta. And so we would have an x coordinate of 2/3, and then you could find the y coordinate using the unit circle equation. And then how would you find tangent? Well, you would just do the y coordinate over the x coordinate, and you should get the exact same answer as we got here, because basically you'll find that y is equal to square root of 5 over 3. And then when you do y over x, they'll simplify to give you square root of 5 over 2. So it works the same either way. Okay, just a few things left. So we're going to look at, although some of these are kind of meatier questions, so maybe I shouldn't say only a few things left. So I wanted to look at a few from number 7. So 7 was simplifying trig expressions. So the first one was asking you to simplify 1 minus tangent squared of x times cosine squared of x, all divided by cosine of x. All right, so let's remind ourselves of what are some of the things that you want to be doing with these kind of problems. So one thing that you want to be thinking about is rewriting stuff as sine and cosine. So that generally will be a good strategy if you have things like tangent, for example, things that you know could be simplified if you kind of multiplied them or divided them by something else involving sine and cosine. Other things that you want to think about are making common denominators, and so there's nothing really to do with that yet. The other thing you want to be looking for is trig identities, so looking for the different Pythagorean identities. And so usually, and this isn't always the case, but I would say in most cases, you first want to rewrite stuff as sine and cosine. I'd say the only real exception to that is if there's already an opportunity to make a common denominator, or if there's already an opportunity to use a trig identity. But oftentimes those things only emerge after you rewrite it as sine and cosine. So we can rewrite this tangent squared as sine squared of x over cosine squared of x, right? Because tangent is sine over cosine, so tangent squared is sine squared over cosine squared. And so we're left with all of this. So now we can see that this expression here simplifies, right? So we're left with 1 minus sine squared of x over cosine of x. So 1 minus cosine or minus sine squared of x, well, that is a trig identity, right? We know that sine squared of x plus cosine squared of x is equal to 1. And so that means that 1 minus sine squared of x is going to be equal to cosine squared of x. And so we can replace 1 minus sine squared of x with cosine squared of x. And so we have cosine squared of x over cosine of x, and that simplifies to just being cosine of x. Okay, so next up, we have, not B, C. So C is cosine of t plus sine of t times tangent of t. So again, in this one, there really isn't anything we can do until we rewrite stuff in terms of sine and cosine. And I guess maybe one thing I should mention going back to this previous one, you could have actually started by splitting this up. So you could have split this up into 1 over cosine of x minus this stuff. And that would have worked as well, but I think it would basically just get you to the same place in a different way. So I'd encourage you to try it that way and see what you get. But yeah, a lot of the times there's multiple ways to do it, and usually the way I'm showing you is probably the fastest way, but that doesn't mean it's the only way. Okay, so let's rewrite this as cosine of t plus sine of t times tangent of t can be written as sine of t over cosine of t. So that means that this is equal to cosine of t plus sine squared of t over cosine of t. Okay, so once you have a fraction introduced like this and you're adding or subtracting things, that's a good hint that you want to make a common denominator. So what would be the common denominator in this case? Well, really our only candidate is cosine. So what we want to do is we want to multiply cosine of t. We're going to multiply it by cosine of t over cosine of t. And then we still have plus sine squared of t over cosine of t. So now we get cosine squared of t plus sine squared of t all over that new common denominator of cosine of t. So as we wrote down above, cosine squared of t plus sine squared of t, we have this Pythagorean identity, which tells us that that is equal to 1. So we have 1 over cosine of t, and another way of writing that would be secant of t. So on these problems, I'm generally looking for, you would definitely get like most of the credit if you left it like this, but I'm generally looking for you to, at the end, kind of return it to the simplest looking expression possible. So, usually at the beginning, you're kind of splitting stuff up into sines and cosines, but at the end, you want to kind of restore it back to other trig functions if that's a simpler way of writing it. Okay, so last one I want to look at from this part is D, and so this one's a little bit different in like the approach for it. So this one is sine of inverse tangent of x. So in a way, this is actually more like the questions that we were doing on the previous page, because so this one is one where you want to actually draw a right triangle. So inverse tangent of x, that's an angle, right? Anytime you're doing inverse trig, that means it's an angle. And so that means that if theta is equal to inverse tangent of x, that means that tangent of theta is equal to x, which is the same as x over 1. And so that means that if you draw a right triangle, your opposite side should be a length of x and your adjacent side should be a length of 1. And so now we can go ahead and draw a triangle. And let's say that this angle here is theta. That tells us that our opposite side is x and our adjacent side is 1. And then you can use the Pythagorean theorem to find the hypotenuse. So basically, if we call this like c, for example, c squared would be equal to 1 squared plus x squared. And so that means that c is equal to the square root of 1 plus x squared, or x squared plus 1. Okay, so now that you have the right triangle drawn, now we can look back at what we're actually trying to answer here. So we're trying to find sine of theta. And so sine of theta is going to be opposite over hypotenuse, which, looking at our triangle here, the opposite side has a length of x and the hypotenuse has a length of square root of 1 plus x squared. Okay, so next up we're going to look at number 8. So 8 was kind of a complicated question, or I shouldn't say that, but it's a question that has multiple parts. And let me actually just make a new page here because we're going to need it. I'll make a couple. I think I'll actually just copy and paste. Let's see. So 8 is here. I'm just going to copy and paste this page so that we have all that info where we need it. Okay. So, number 8. So this is kind of like, on both of the previous tests you've had, there's been a question with like the unit circle where it's like a little more abstract, where you're not really given the angle. And this is kind of like that. Notice that, and I made a note of this on your second midterm. There's a question where I really intended for you to do it without using a calculator, but I didn't specify that. So some people used a calculator and actually found the angle. If I give a question similar to that on the final, I'm going to expect that you know how to do it without finding the angle. So that's how I'll go over this question. Okay, so the question says, suppose that inverse cosine of 3/4 is equal to theta. So the first thing we want to do is graph the angle theta on the unit circle and provide the x coordinate and y coordinate of its terminal point. So let's start by doing that. So number 8 tells us that inverse cosine of 3/4 is equal to theta. And so on part A, we're going to graph something on the unit circle. So let's think about how we're going to figure out how to draw this. Well, if inverse cosine of 3/4 is equal to theta, that means that cosine of theta is equal to 3/4. But there's multiple angles, actually many angles on the unit circle where cosine is equal to 3/4. So we need to get a little bit more specific here. Because we're doing inverse cosine, that means that theta is between 0 and pi, because theta is really like coming from inverse cosine. And so that means that it has to actually be in quadrant 1, right? That's the only place we're going to find an angle where the x coordinate is 3/4 and it's between 0 and pi. So maybe let's estimate it's here. And so this is our angle theta. And so because inverse cosine of 3/4 is theta and cosine of theta is 3/4, that tells us that the x coordinate is 3/4. And then you can find the y coordinate using the Pythagorean theorem, and you should get square root of 7 over 4. So I'll just make a note here that this comes from Pythagorean theorem, or it's really like the unit circle equation. So this comes from the fact that x squared plus y squared is equal to 1. Okay. So that's answering part A. We've graphed something on the unit circle. And I know actually the way I drew it is actually not really great. If you look at the solutions, and maybe I'll fix this. The angle is actually kind of a little bigger than you would expect it to be. And if you look at the solutions, I actually provided like a grid, so you can actually see that the point that I drew is at an x value of 3/4. And I know it looks like it's a 45-degree angle, but it's actually not. Okay. So the next question asks us to find sine, cosine, and tangent. So this is basically just asking you to, use the definitions of sine, cosine, and tangent. So sine is going to be equal to the y coordinate that we found. So that's square root of 7 over 4. Cosine, we already know that that is equal to 3/4. And then to find tangent, we do sine over cosine, and so that's going to be square root of 7 over 3. Okay, so next question is asking us to find sine and cosine and tangent of negative theta. So there's a couple ways to do this. One is to be aware of the even and odd identities. So we know that sine is an odd function. And so sine of negative theta is going to be the opposite of sine of theta. So it's going to be negative square root of 7 over 4. Cosine is an even function. So cosine of negative theta is going to be the same as cosine of positive theta. So you get 3/4. And then tangent is also odd, so it's going to be the opposite of tangent of theta, and so it's going to be negative square root of 7 over 3. Another way that you could answer this is if you just kind of think about what this looks like, negative theta is going to be here, right? And so the x coordinate is still going to be 3/4. The y coordinate, though, is going to flip. And that's really that's the reason for these even and odd identities. So you could do it either way. And they're not really different ways. They're actually the same way. I feel like it looks like I wrote 9, so let me rewrite that as 4. All right, so next question is asking you to find sine of pi over 2, or sorry, theta over 2, and cosine of theta over 2. So this is asking you to use the half angle formula. So the half angle formula for sine is plus or minus the square root of 1 minus cosine of theta. Sorry. So they both involve cosine, basically because of where this formula comes from. So if you remember when we first kind of came up with this formula, it actually came from the double angle formula for cosine. And then one of them ended up being plus and one ended up being minus. So basically all you have to do for this is plug in what we have for cosine of theta and then figure out whether it's positive or negative. So what was cosine of theta? Well, we know that cosine of theta was equal to 3/4. And so we have 1 minus 3/4 divided by 2. So that is going to simplify to plus or minus square root of, so 1 minus 3/4 is 1/4, right? You don't even really have to do any arithmetic for that. 1 minus 3/4, you're left with 1/4. And then we still have 2 in the denominator, and so that's going to give us plus or minus square root of 1/8, which can be written as 1 over square root of 8. And square root of 8 can also be written as 2 root 2, although I would be fine if you left it as 8. So is it plus or minus? Well, in order to answer this, what we need to do is look at our picture and look at, is sine of theta over 2 positive or negative? So theta is the angle in magenta, so theta over 2 would be like here, right? So the y coordinate would still be positive, the x coordinate would still be positive. So that means that sine and cosine of theta over 2 should both be positive. And so that tells us that we can take the positive. So very similarly here, if you do the same thing, but for the cosine half angle formula, you're going to get plus or minus square root of 1 minus square root of 7 over 4, because, or sorry, I don't know why I said that. It's still cosine, sorry, I spaced out for a second. So we're doing 1 plus 3 over 4. So only difference is that we're adding instead of subtracting. And so what is 1 plus 3 over 4? Well, that's going to be 7 over 4 if you make a common denominator. So we have 7 over 4 over 2, and that's the same thing as 7 over 8. And so honestly, it would be fine with me if you left your answer like that, but we could also rewrite this as plus or minus square root of 7 over 2 root 2. And then again, this one is positive because we saw that theta over 2 had a positive x coordinate and a positive y coordinate. Okay, so there's a couple more things. So next thing was finding sine and cosine of 2 theta. So basically, this is just very similar to what we just did. It's just using different angle formulas. So to find sine of 2 theta, that's the double angle formula. So that's 2 times sine of theta times cosine of theta. And then the double angle formula for cosine is cosine squared of theta minus sine squared of theta. So we know that sine of theta, we already figured out that that was square root of 7 over 4. We already figured out that cosine of theta was 3/4. And so if we put this all together, we're going to get 6 root 7 over 16. And that can be reduced to 3 root 7 over 8. And then similarly here, if we do cosine squared of theta, so that's going to be 3/4 squared, minus sine squared of theta, that's going to be square root of 7 over 4 squared. That's going to give us 9 over 16 minus 7 over 16, and that's going to equal 2 over 16, which is the same as 1 over 8. So it's really just kind of using these formulas, plugging stuff in. So next part is asking us now to find sine of negative 2 theta and cosine of negative 2 theta. And so this is just testing you again on the even and odd identities. That's all this is doing. So sine of negative 2 theta is going to be the opposite of sine of 2 theta. So we just figured out in the previous question that sine of 2 theta was 3 root 7 over 8. And so that means it's going to be negative 3 root 7 over 8. And then cosine is an even function. So cosine of negative 2 theta is the same as cosine of 2 theta. And we just figured out that that was 1 over 8. All right, now we're on the last question for this one. So the last question asked you to find sine of theta plus pi over 6, and then cosine of theta minus pi over 6. So this is testing the that you're able to use the angle addition and subtraction rules. So how did the rule work for sine? Well, basically it says that you do sine of theta times cosine of pi over 6. So you're kind of you're mixing and matching, plus cosine of theta times sine of pi over 6. Now you can just fill all this in with everything you know. So we know that sine of theta is square root of 7 over 4. We know that cosine of pi over 6 is square root of 3 over 2, just by going on the unit circle to an angle of pi over 6. We know that cosine of theta is 3 over 4. And we know that sine of theta is 1/2. And so altogether, we're going to get square root of 21 plus 3 over 8. Okay, so how does the formula work for cosine? Well, for cosine, you actually put together, so you have so here you're kind of mixing and matching, right? So for cosine, and I'll give you, by the way, these formulas on the test again, but for cosine, you're doing like both of them at once. So we have cosine of theta times cosine of pi over 6. And so why did I not put a negative? Well, so how does the subtraction rule work for cosine? So it's just like the addition rule, except for that you kind of flip the sign in the middle. And so the reason for that is basically that you could say cosine of negative pi over 6, but cosine is an even function. So there's no reason to put that negative sign there. But then when you get to the second part where you're doing sine, so normally for the addition formula, you would have a negative sign here. But what will happen, I'll just write it out this way first, you would have sine of theta times sine of negative pi over 6. But sine is an odd function, so what you can do is take this negative sign out of here and put it here. And so if we put this all together, we know that cosine was equal to 3/4. We know that cosine of pi over 6 is equal to square root of 3 over 2. We know that sine of theta was square root of 7 over 4. And we know that sine of pi over 6 is 1/2. And so putting this all together, we get 3 root 3 plus square root of 7 all divided by 8. All right, so the last thing we're going to do is some solving of the trig equation. So a few that people requested from part 9. So First one we're going to look at is 9f. So 9f says cosine squared of x minus sine of x times cosine of x is equal to 0. And so in this question, by the way, we're specifically trying to find all solutions between 0 and 2 pi. So one thing that I just wanted to mention is that make sure that you're really looking at what the question is asking for. So you shouldn't, in this problem, write plus 2 pi k, because the question isn't asking for all solutions. It's only asking for solutions between 0 and 2 pi. And the reason I kind of mix up, like when I'm asking you all different ways, is I want to make sure you understand what you're doing. And if you're just kind of blindly tacking on plus 2 pi k, that tells me that you don't really understand what that means. So adding plus 2 pi k is a reflection of like when you're trying to describe all solutions. It's saying, well, here's some solutions, but you could also go around the unit circle as many times as you want and get another coterminal answer that would also work. So here we don't need to do that because we're only looking at solutions between 0 and 2 pi. Okay, so how do we get started on this? We want to start by looking at our equation and basically seeing, what makes sense to do first. So I guess what I mean by that is in some problems, so let's say that you only had, and maybe let me actually go back and point some out here so we can kind of compare and contrast. So for example, if you're solving A here, so A says 4 times cosine squared of x minus 1 is equal to 0. So because that equation doesn't have any other trig functions in it, it doesn't have, it doesn't look like h here. So h has only cosine, but it's like cosine squared and another cosine. Though things like the one that we're working on now and h, those involve factoring. But something that looks like a or b or c or d or e, none of those you have to factor because you only have one trig function kind of by itself. So in those cases, you want to start by isolating your trig function. But for everything, basically, I think from F through J, those are all going to require factoring. So for F, we want to see what can we factor out from both things. And that's generally going to be your first step on here. So what can we factor out from both of these? We can factor out a cosine of x. So if we factor out cosine of x, we're left with cosine of x minus sine of x is equal to 0. So anytime that you're solving by factoring, you want to set each factor equal to 0. So either cosine of x is equal to 0 or cosine of x minus sine of x is equal to 0. So where is cosine of x equal to 0? Well, that's going to happen when we have an x coordinate of 0. So one possible answer would be here, right? So if we go to an angle of pi over 2, that would be one possible solution. And then another angle that would work would be 3 pi over 2, right? Because if you go to an angle of 3 pi over 2, it also has an x coordinate of 0. So cosine is also equal to 0. So we already have two solutions. So this next part is a little bit trickier to solve. So cosine of x minus sine of x is equal to 0. So there's a couple different ways to solve this. What I think is the easiest way is to think about, okay, well, if cosine of x minus sine of x is equal to 0, that means that cosine of x has to be equal to sine of x. And so that means we're looking for angles where the x coordinate and the y coordinate are the same. So what's an example of an angle where that happens? Well, pi over 4, right? If you go to an angle of pi over 4, sine and cosine are the same, right? They're both square root of 2 over 2. So you might think that 3 pi over 4 would also work, but in that one of them is negative, one is positive, right? So that actually doesn't work. So the only other angle that's going to work for that would be here, this angle, which is, let's see, that's 5 pi over 4. Because when you go to x is equal to 5 pi over 4, that has both sine and cosine equal to negative square root of 2 over 2. Another way that you could do this is if you take this at this stage, if you divide both sides by cosine, you get sine over cosine, which is tangent, is equal to 1. And so really it's the same as solving the equation tangent of x is equal to 1. Okay, and that's it. We have found now all solutions between 0 and 2 pi. All right, so there was also a request for part H. So H is asking us, and let me just grab, oops, another unit circle. So for H, we're trying to solve cosine squared of x minus cosine of x minus 2 is equal to 0. So this one is what's called a quadratic in cosine, right? So there's a kind of a shortcut that or not a shortcut, it's actually a long cut, but a trick that I showed you, which was instead of writing cosine of x, you can say, okay, let's let u equal cosine of x. And that might help you kind of see how to factor it. Because then this whole thing can be factored as, or can be written as u squared minus u minus 2 is equal to 0. And then you can just focus on factoring that, which I think is a little less intimidating to factor than something with cosines. So how does this factor? Well, we would want to have, we need to have a u and another u to get a u squared. And then we want to have negative 2, and we want to make sure we end up with a negative u. And so the way that we can do that is u minus 2 and u plus 1. And so you can kind of go back to cosine at any stage, but if you want to, you can still kind of go from here and say, okay, that means u minus 2 is equal to 0. And so that would mean u is equal to 2. And then over here we have u plus 1 is equal to 0. And that would give us u is equal to negative 1. And so putting that back in terms of trig stuff, that means that we're solving two equations. Cosine of x is equal to 2, and cosine of x is equal to negative 1. But if you don't care about doing this whole u thing, you don't have to. Like, you really could have just factored this from the get-go, as you could have written cosine of x minus 2 and cosine of x plus 1, and you would get the same answer either way. Okay, so let's solve each of these equations. So cosine of x is equal to 2. That is going to have no solutions, right? Because there are no values, no angles that you could plug in that would make cosine equal 2. So this next part, we have cosine of x is equal to negative 1. So that means we're looking for angles where the x coordinate is negative 1. And so the only angle that's going to happen at is pi. And so this actually only has one solution in the interval from 0 to 2 pi, which is pi. So I wanted to also look at, let's look at, I'm debating, no one requested these, but I wanted to look at either I or J. Let's do, sorry, I'm just debating which one to do. Let's do J. They're pretty similar. So J is asking us to solve e to the x times cosine of x minus cosine of x is equal to 0. So this is another factoring problem. It's just that now we have not just trig functions, but another function kind of blended in. So what can we factor out from both of these? Well, they both have a cosine of x. And so if we factor out cosine of x, we're left with e to the x minus 1. So now we want to set each part equal to 0, same way that we always do. So either cosine of x is equal to 0, or e to the x minus 1 is equal to 0. And so where is cosine of x equal to 0? Well, this one we already talked about, right? So that happens at an angle of pi over 2. So x could be equal to pi over 2. Also happens at an angle of 3 pi over 2. So x could be equal to 3 pi over 2. And then what about over here? Well, this would be e to the x is equal to 1. And then what number is going to make that true? Well, that would require that x is equal to 0. So these are our three solutions. And you don't need to think of x as an angle, but it could be, right? So like, for example, what would happen if we plug this in? You would get e to the 0 times cosine of 0 minus cosine of 0. So what would that be equal to? Well, e to the 0 is 1. Cosine of 0 is 1, so we get 1. And then cosine of 0 again is 1, and so we get 0. And that's exactly what we're trying to solve. So you can always check your answers on these, right? By plugging the angle or the number, the solutions that you get back in and verifying that you actually get what you're supposed to get. Okay, so last example that we're going to do, and again, I have to copy and paste this. Okay, so the last one we're going to look at is one where it has a different period. So it's not just going to be sine or cosine of x. This one we're going to do is going to be k. And so this one is 2 times sine of 3x is equal to, or sorry, plus 1 is equal to 0. So because this one doesn't involve any other trig functions or anything else to really factor with, we want to just start by isolating the sine part. So we can start by subtracting 1 from both sides, divide both sides by 2. And so now we have sine of 3x is equal to negative 1/2. And so this is another case where basically, and you don't have to do it like this, but you can think of, okay, 3x is an angle, right? It's 3 times something, but let's just kind of group that together and think of it as an angle. And so we can say, let's let u equal to 3x. And so that means that we're solving now sine of this angle u is equal to negative 1/2. And so we can start by figuring out what u has to be, and then we can use that to figure out what x has to be. So what angles would work here? What angles would have sine equal to negative 1/2? Well, one possibility would be the angle 7 pi over 6. So one possibility is that u is equal to 7 pi over 6. Another possibility would be over here. And let's measure it as a positive angle because, again, we're looking for solutions between 0 and 2 pi. So it doesn't really make sense to come up with negative solutions. So this angle would be 11 pi over 6. Okay, so how do we now kind of translate this in terms of being, like, we just found u, but we don't want u, we want x. So how do we finish this off? Well, we basically just go back and write 3x. So 3x is going to be equal to 7 pi over 6. And so if we divide both sides by 3, that tells us that x is equal to 7 pi over 18. And then similarly over here, if we say 3x is equal to 11 pi over 6, that tells us that x is equal to 11 pi over 18. So that tells us two possible solutions, but there's a little bit more that we have to do here. So really the reason that we have to do a little more work here is because basically the function that is involved here, the sine of 3x, that has a period that is different from 2 pi. And we're looking for, in this case, all solutions between 0 and 2 pi. And so we need to basically figure out what the period is of this function and add those onto our solutions. And any solution that we get that lies between 0 and 2 pi is going to be a valid solution. So basically what we want to do to come up with our further solutions is stuff like this. So we could say next that x is equal to 7 pi over 18. So what is the period of this function? So if you have sine of 3x, that's going to have a period of 2 pi over 3. And so what we can do is instead of adding 2 pi, we can add 2 pi over 3 and see what we get. So that would give us, I don't know why that is just freaking out right now and coming up so much. But 7 pi over 18 plus 12 pi over 18, if we make a common denominator, and that would give us 19 pi over 18. So that's another possible solution. So far we have 7 pi over 18, we have 11 pi over 18, we have 19 pi over 18. And notice that those are all between 0 and 2 pi, right? They're not going to be over 2 pi until we get to like 36 pi over 18, if you think about how those fractions work. And so we can actually keep going. So we can add another set of 2 pi over 3. And we basically can keep doing that until we get things that exceed 2 pi. So here we could say x is equal to now 19 pi over 18 plus 2 pi over 3 again. So that's going to be 19 pi over 18 plus, so now if we make that common denominator again, we get 12 pi over 18. So that gives us, what is that? That's going to be 31 pi over 18. And so that's as far as we can go. If we tried to add another 2 pi over 3, then we would exceed 2 pi, right? And we're looking for solutions between 0 and 2 pi. Okay, so those both are, so these angles that we just found here, those came from this originally, right? Those were by taking that solution and adding the period as many times as we could before we ran out. So now we're going to do the same thing, but with 11 pi over 18. So I don't know which colors I haven't used yet here. I guess I'll use this one. So we could get another solution by saying x is equal to 11 pi over 18 plus 2 pi over 3. So that's going to be 11 pi over 18 plus, so we make a common denominator, that's going to be adding 12 pi over 18. And so that gives us, that's, sorry, my brain is tired, 23 pi over 18. And then we can do it again. So now last one, I think, we're going to take 23 pi over 18 and add 2 pi over 3. So that's going to be 23 pi over 18 plus 12 pi over 18, and that's going to give us 25 pi over 18. And you could try to add 2 pi over 3 again, but you would see that you would end up exceeding 36 pi over 18, so exceeding 2 pi. And so just to kind of make that same connection we made up here, and I feel like I've totally run out of colors. I guess I'll use black. So these two solutions here came from this one here. So I don't want to say they're coterminal because that doesn't really make sense, but they're kind of like coterminal because the period in this case is not 2 pi. It's 2 pi over 3. They're kind of also solutions for that reason. All right, so hopefully this was helpful to you. And like I said, tomorrow's video will focus on questions related to finding like polar coordinates and stuff like that, and then conic sections, as well as the 141 review questions. All right, I'll see you then.